All right, thank you. So this session, we're going to hear from our 6 seed projects that were funded in year 4. So they've been funded for a year. We're going to hear what happened in those seed projects. As Scott mentioned this morning, seeds are a way that we let new ideas sort of get some support in SpectrumX. The idea is that they are a seed, that this is sort of the start of something that hopefully will lead into something bigger, maybe a external proposal. Maybe they'll become part of one of our flagship projects. We hope to see something come out of the seeds. So we hope that they all grow and blossom. So we have 6. We have an hour to do this. So I'm asking each person to keep their remarks to around 7 or 8 minutes. So we do have a couple minutes for questions on each one, if possible. And we're just going to go in order. The first one is this project that Mariya is going to present. So Mariya.
Can you hear me okay? All right. Hi, everyone. So today I'm going to talk about multispectral transmitter analytics. So kudos really go to the one who's not bolded in this list of names, my students Vasu Tanika and Andrew Koro, who are here, and Clark Mattoon, who was an undergraduate student for about 1.5 years and is transitioning to do their PhD in our lab as well. So when I say multispectral transmitter analytics, so we've begun to look at spectrum occupancy as a multispectral phenomenon. So when you have a transmitter or receiver that are licensed to operate on a particular spectrum, inevitably they produce stuff outside of that licensed spectrum. Things like harmonics, things like spurious emissions, sideband leakage. So all of that kind of we think about as a multispectral footprint of spectrum activity. So within the SEED project, we're particularly focusing on harmonics. So harmonics are replicas of a transmitter's fundamental frequency activity across integer multiples of that fundamental frequency. And so our goal here is to be able to detect harmonic activity and reconcile it somehow automatically with whoever caused the harmonic activity. And this has applications widely in spectrum enforcement because harmonics have been shown to interfere both with passive scientific users who are very, very sensitive, as well as with active technologies. So the key questions to harmonic detection and reconciliation are, first of all, given an arbitrary observed spectrum activity, how can we know whether it's a fundamental signal or a harmonic? And then if it is a harmonic, how do we determine which order is that harmonic? And then the second question is, harmonics are really, really faint. So they're supposed to be non-existent. They're suppressed by hardware, around the fundamental frequency. So the question then becomes, how do we characterize the time frequency footprint of those ultra-low signal-to-noise ratio harmonics, and potentially do that in the presence of high signal-to-noise ratio incumbents that might be active in a band where harmonic occurs. So 2 questions, really. The first being, is this a fundamental or harmonic that we're observing? So the key intuition behind this is that depending on what order harmonic you might be observing, the activity across multiple spectra will follow some sort of a unique pattern. And so the idea here, or the intuition here, is that we will perform multispectral measurements. So think about a multi-headed sensor that simultaneously observes across multiple spectra of interest that might be candidates for a particular activity to be a harmonic. And in this particular case or project, we're focusing on using power spectrum density measurements. Then we would characterize the time frequency footprint of individual observations across the spectra, and then reconcile based on some similarity measure, to determine whether things look alike and arise from the same fundamental activity. And the challenge that emerges here is harmonic activity is faint, how to detect and characterize it, especially in the presence of high power incumbents. And really the intuition there is that we cannot do that directly in raw spectrum traces. So part of what Andrew and Vasu have been looking into is, given this multispectral input data, how to characterize it, and how to aid accurate characterization by the use of generative AI, particularly diffusion models that can be used for denoising and enhancement of poor quality images traditionally, and now we start exploring this in the context of spectrum traces. And then having aided ourselves in characterizing what the activity looks like across spectra, then use these co-occurrence patterns across the multiple spectra joined with similarity measure in order to both detect whether that's a harmonic or not, and then determine which order harmonic are we observing and reconcile it with the culprit for that harmonic. So I'll stop here in terms of methodology. Vasu has a poster this afternoon. So if you're interested in exploring more the ins and outs of the methodology, we'll be there, so stop by. I wanted to touch a little bit on what we've done to evaluate this first stab at the algorithm. So we've done qualitative as well as quantitative evaluation, and we're looking really to detect to determine how accurately we're able to detect accuracy as well as classify the type of harmonic or the order of harmonic that we're observing. In quantitative evaluation, we help ourselves to a synthetic data generator that we wrote up. And then in terms of qualitative, in the wild evaluation, we've run both in-lab testbeds within a small sort of footprint, as well as later this past summer, we did a measurement campaign at the National Radio Quiet Zone around the Green Bank Observatory, which is a great place to hunt for harmonics because it's currently quiet. So if there is something, it shows up. All right, so in the last minute that I have here, just a couple of highlights. We look to be able to accurately detect harmonics within our synthetic setups, both with the presence of incumbents and without, and especially in the presence, in the lack of incumbents. And denoising aided by these generative AI models seems to help, particularly with faraway harmonics, which are trickier to detect. We are able to classify to a large degree the order of harmonic. This is what our in-lab testbed looked like. It was basically really controlled transmission across, certain distance across the hallway, where we were able to compare with counterparts and show that we're able to detect up to fifth harmonic. But really what I wanted to highlight is some of our efforts within the National Radio Quiet Zone and around the Green Bank Observatory. So we had built out a multispectral sensor, really a prototype, needs a lot of improvements, and we've learned some lessons from this measurement campaign. But we were measuring across different locations in the NRQZ, particularly targeting public safety stations that are, open and decodable. And here are a couple of examples of harmonics that we're actually able to catch as we were doing these campaigns, and what will keep us busy, data set that will keep us busy for more detailed characterization moving forward. So in terms of next steps, more data to be analyzed. If you have a harmonic problem, we'd love to measure that and continue expanding on those real-world use cases. And this is now becoming a component of the flagship Project 2 efforts that SpectrumX is undergoing. So a couple of recognitions of all the people who helped us with the GBO experimentation. And I think with that, do we have time for questions?
Maybe one quick question?
Yes.
Oh.
Thank you for the presentation. The technical challenge that you present is that these harmonics are really faint, and the way you phrased it was ultra low SNR regimes, right? If the signal strength of the harmonic is so low, why should we care? Probably the incumbent or whoever transmitting is within their emission mask, right? So that's why it's so low. Yeah. And if that's the case, everybody is doing the correct thing. Yeah. Why should we care about detecting the harmonics? Thanks.
Right. Yeah, that is a great question. So why should we care? Some technologies tend to care more than others, and that really boils down to the sensitivity of these technologies. So if a harmonic erroneously falls onto a radio astronomy band or remote or sensing band, I'm pretty sure, there's the masking requirements there are much harder to be met. But there are cases where harmonics erroneously fall on things like cellular communications, so like FM radio, fifth harmonic, I think, falling on, or seventh, falling onto the upper, close to gigahertz band in cellular communications. So those are also, cases in which we'll want to be able to detect and reconcile in cases where you actually fail to meet your masking down requirement. So, yeah, I think
Al has a question online, if we have time for one more.
Let's sure.
Yeah, I've got a question, Mariya. Seems like with harmonics, there's an excellent opportunity to use phase information, in which case the coherency of the harmonic with respect to the fundamental can be taken advantage of. And I think you could get a much higher detectability that way. I'm just wondering if you thought about doing that.
Yeah, so for everyone, it was a bit faint, but I think what Al's question is boiling down to is how can we use phase information and coherency between the fundamental frequency and harmonic bands as a feature to basically as a similarity feature. Great point. Not something that we've considered yet, but certainly the concept and the framework can be turned around to, that would essentially redefine the input into the framework and can either serve as an added feature or maybe as a replacement to the input that we've been doing so far. But yeah, great point.
All right, let's thank Mariya.
Thank you.
Move onward. So our next seed project is going to be presented by Dongning, who is joining us remotely. Okay, so Dongning, I'll let you take it away.
Yeah, can you hear me all right? Do you hear me? I just want to make sure that.
Yeah, we can hear you.
We can.
Okay, thank you. This is a seed project on operator self-identification for spectrum sharing. Most of the work is done by my PhD student, Lina Liu. And this is together also in discussion with Igor and also Chandra. Krishnamurthy is a professor in India. He visited us for some time. And we had a lot of discussions in the process of proposing this project. And he has given us also some good advice over time. Okay, so the motivation of the project is largely that we think that in a shared spectrum, today's mode of operation is like driving on highways, on shared highways without license plate. So whenever I don't know, can you flip to the next page? Help me do that. I don't think I can do that. Thank you, Randy. So what is the purpose of having license plates, right? So if there is any accident or any collision in the information highway, we'll have a way to find out who are responsible for this. And in particular, in the case where we share resources, we will know who are the parties that got involved in this collision. So it's unimaginable, and when a car, so to get today's mode is usually when a packet is destroyed or we will just resend it. It's hard to imagine on a highway when a car is totaled, we just send another car. So so that's the sort of the thinking that we had, which is to say that in shared spectrum, it would be nice if anything happened, we're able to know who are the responsible operators. And next page, please. And so there comes our proposal to embed operator IDs in transmissions. Not necessarily in every single packet, but every now and then, a transmitter will identify itself. And also the identification is not necessarily as detailed as who exactly the transmitter is, but rather who the operator is. So let's say Verizon's devices will tell us that's Verizon. So basically who is orchestrating transmission over that spectrum. So this may yield a few benefits. One of them is to facilitate coordination between coexisting operators in shared bands, for example, in 7 gigahertz. And also to identify interfering operator in some other applications, let's say scientific applications, where a radio astronomy may want to know who might be the other operator that leaks into the spectrum, including, say, in the example that Mariya talked about, which is the harmonics that's leaked into another system. So the challenges here are that usually we wish to be able to still identify the operator when we don't necessarily understand which spectrum, what is the entire spectrum band that the other operator is operating, because we don't know who that is to begin with, and we don't have, let's say, information about how to synchronize to that transmitter and how to compensate for frequency offset, timing offset, and all of these things. We don't have information about the modulation and coding scheme of the interfering transmitter. So that's part of the challenges, and the other issues are that we would like that whatever solution we have to have low overhead in terms of energy, bandwidth, and computation. So in the sense that adding an operator ID is going to use part of the transmitter's energy, and it's going to use part of the bandwidth, and also in the process of encoding and decoding, it's going to cost us also computational resources. Next page, please. So here's the sort of a general picture, high-level picture of what we're thinking about. So let's say there are two operators. Here we're only looking at two links, and there is transmitter P and transmitter Q, and the two operators orchestrate their transmissions. And at some point, a receiver P receives, of course, both signals, and usually the interferer comes in weaker, and there's a receiver P, both receiver P and Q. And the two operators may operate at two different pieces of spectrum, but with some overlap in between. So that overlap may be the entirety of operator P's spectrum or part of it, and which is not known to the other operator to begin with exactly what is the whole band the other operator is operating over. So generally, we can divide radio spectrum into subbands, let's say 10 megahertz subband. That's the Bs that are identified here. And operator P occupies many of these subbands. Operator Q occupies many of these subbands. And certain transmissions may overlap by part of it, and we hear there is a segment of intersection between operator P and operator Q's transmissions. What we wish to do is for an operator P, for example, to be able to conduct its own data transmission, and at the same time, if there is a certain amount of interference, it will be able to use, based on a signal in the overlapped spectrum, to decode operator Q's ID. And operator P is generally not interested in the data of the other operator, and in fact, it will generally not be able to decode the data, but it will wish to decode the operator's ID. So that's the question. And next page, please. So, well, I guess the PDF is not displaying perfectly here. So the proposal here, one technique that we considered and we are proposing here is to use a watermark. So essentially, a transmitter on top of its data transmission will also add a watermark to its transmission that is a lot weaker than its data transmission. Here we're thinking of using, let's say, 1% of the energy. So in effect, the watermark is like 20 dB below its own data transmission, and it's periodic in frequency and in time. And as long as the two operators overlap in one of the spectrum periods, let's say 10 megahertz, it is sufficient for decoding the other operator's ID. And it is not interested in the data. And in fact, the one operator, say operator P, when it's trying to decode operator Q's data, it will only use its own data samples that is synchronized to its own data transmission with its own frequency and timing offset compensated, and that usually yields a certain timing and frequency offset relative to the other transmitter. Nonetheless, because the transmissions are periodic, we can still use coherent combining in time periods to improve the SINR of the watermark. And here is sort of an illustration of one design that we have for the watermark, which is to add a little of signal to some subcarriers in our OFDM transmission. Basically, if you think of it, let's say two additional tones, on top of two additional tones, there is some periodic signal that we keep transmitting. So that's part is inspired by, the telephone dials are a combination of two tones usually that tells us which numbers we're dialing. And that's why a simple analogy to what we're doing here. And the bottom picture is the data transmission to plus the watermark. So most of the signal looks like basically the watermark, the data transmission. The watermark is not immediately obvious from the signal, and it is through some signal processing that we're able to identify to decode the ID. Next page, please. And here, basically, a receiver only synchronizes to its own transmitter and decodes and its own data. And it can, here we make a few assumptions that it can cancel its own signal first, and the timing and frequency offset relative to the other transmitter are not compensated before sampling. Right? So it will sample its own useful signal. And after the sampling, it will try to use signal processing to estimate the frequency offset relative to the other transmitter, and use hypothesis testing also to decode the other transmitter's ID. Now, our assumption is that the ID is only a very small number of bits, let's say 10 bits or something like that, which we could decode without a coherent detection. Next page, please. So here's just in I'm showing one simulation result. So here, data uses 99% of energy, and ID uses only 1%. And in the absence of its own transmitter signal, if we just listen to the other signal, then the SNR of the other transmitter's watermark is minus 23 dB. And here we graph the probability of decoding error and versus the number of frames that we use, basically how many ID repetitions we need to decode to a certain level of accuracy. There is one parameter here, that's the rho. It stands for the interference receiver's power relative to the receiver we are interested in. What is the difference between their power? So here, either there is no data that we are interested in decoding for ourselves. In that case, the performance, of course, is better because all that we hear is the other transmitter and its ID. Or our own transmission is in fact stronger. That's when we can decode our data and then cancel our own signal cleanly. And that's the two situations there that yields better performance. But by and large, we can decode, here I think it's 10 bits of ID. We can decode the other IDs with reasonable reliability, that let's say 1 in 100, after we have about 100 repetitions of the received signal. Here we're simulating a relatively, I think, realistic scenario. Next page, please. So in terms of future work, we would like to further evaluate let's say on the policy side, we are interested in understanding why would anyone adopt this strategy, and we can think of a few ways of doing things that the multi-operators might decide to voluntarily include their IDs because the facility benefits all of them, and there might be some game theoretic formulation there. And also, it could just be an industry decides to have a standard over a certain part of a shared spectrum, so that in order to share very well, we need to include some ID information. And further, it could be just a regulatory mandate. So we would like to study, the policy aspect of this proposal. And also, we would like to validate the proposed technique using SDRs and MEPs. We'd like to analyze the fundamental trade-off between overhead and identification accuracy. What we have done is that we proposed one signaling, but we'd like to know, if regardless of what signaling, what is the ultimate trade-off there. We'd like to also explore operator coordination mechanism using additional signaling bits beyond just operator IDs. So if I have a few more bits that we can embed in our transmissions, is there anything else the operators can do to facilitate sharing? That's all I have, and thank you for your attention.
All right, thanks, Amy. So I think in the interest of time, we'll take questions offline for Dongning and move on to the next speaker, which is Caleb. All right.
Thank you, everyone. My name is Caleb Reinking, and I'm with the University of Notre Dame, and we were awarded a small seed project award to work on bringing the SIGCAP data that many of you are familiar with. So they're on cell phones like this. They're used with the broadband MapUs Broadening Participation Project, and they've gone out to multiple universities. And our project was to work on that, and I will tell you a little bit more about it. My co-PI is Manisha Ghosh. And then we worked regularly with her graduate or postdoc, Mohammed Rahman. So here's the big idea. We wanted to convert a prototype that Mohammed had written that would take this SIGCAP data, that's just time series data about signal strength and using all the antennas in the cellular device to be able to map that. And we wanted to take a prototype that was working on his local machine that he had developed and provide it kind of to the world. So convert a prototype of the SIGCAP visualization into publicly accessible, into a publicly accessible, interactive data sharing platform to scale SIGCAP visibility and impact in both research and broadening participation workforce development contexts. So what we found was that there was a treasure trove of data sitting in a Google Drive folder, and how could people interact with that, and how could people use that, and how could we better visualize and have a quicker feedback loop from the point of data collection to visualization, which could lead to maybe some broader questions that might be able to be asked of the data. So the pre-seed state is there was the SIGCAP mobile application, which has been used for years and is used across the broadening participation projects. And here's a description of it from the SIGCAP website. SIGCAP is an Android app that simultaneously collects phones' GPS data as well as cellular and Wi-Fi information using only the Android API without requiring root access on the device. And then the visualization prototype state, Mohammed had developed an app that could pull SIGCAP data out of the cloud store that it was in and display it on an interactive map and then allow you to download it in various formats. So here's what we built. So you've seen the bottom right screenshot before in the earlier slide deck that Scott was showing. But we have this publicly available now. We have finished this work. Now, it is not perfect. It is a seed. So it works, and I think that it's helpful to people. But it's now available at a SpectrumX.org domain. So it's sigcap.spectrumx.org. There are 16 million discrete data points that are now available on that website over the course of about 4.5 to 5 years worth of data uploads. So we retroactively loaded in all the broadband MapUs data and now have it available here. The data comes in hourly, so we saw Manisha uploading some data earlier from this room, and it's now available on the site. So if anybody wants to see what the 2.4 or 5 gigahertz Wi-Fi signal strengths are in this room, we have that available now. And then users, anybody can sign up for an account. It does go through an approval process, mainly because we want to know who's signing up for this thing so that we can reach out and ask questions and follow up. So it does do that, but anybody can sign up for an account there. And users can self-serve there. So you can filter data to regions of interest. You can view the data on a map. You can kind of do some basic exploration of the data on the map. But then we know that this platform is not going to be your heavy lifter on the data analysis side and the research side. So at the end of the day, you're probably going to get to the data that's of interest to you and then download it for offline processing. Here's a QR code if you would like to go there. In the spirit of just making it shareable, I will tell you this, we did not optimize any part of this for mobile, okay? So you're gonna go there and the front page is pretty good, but then get there on a desktop machine if you wanna actually explore the data. Mohammed will have a poster at the poster session to talk about the work around SIGCAP and I think a little bit about this data platform. But even better, we will have a table at the poster session where myself and my colleague David will be sitting there with laptops and displays, one of which will be running the SIGCAP data platform, and then the other one for the SDS that you've heard about through the flagship Project One. So stop by, we're there to help onboard, sign up for an account. I'll have a phone there if you want to take some data, upload the data, see the data on the website kind of in real time. So we would love to talk with anybody that's more interested in this. Seed funding has led to a few outcomes, so I wanted to share those with everyone. So we did submit a response to an FCC NOI that was talking about publicly available neutral data sets that might be interesting to the FCC in the future. Mohammed has done a poster at AeroFest. We will be giving a demo of this platform at the Gateways 2025 conference, which is more of like a scientific platform, scientific gateways conference, but my group is a research software engineering group, not necessarily a radio domain group. So this is the Scientific Gateways Conference is great for our group to go present it. We did identify an NSF IDSS planning grant target. So that's the external grant that we're going to be going for to be able to do a planning grant period to say, what would this look like to scale out and make this tied into some federally available federal data sets. We will be increasing engagement with Broadband MapUs. We have talked with Mariya and we've talked about, we're going to present to that group at the next group meeting and talk a little bit about our work there. And then multiple news articles coming out of SpectrumX and Notre Dame. One that isn't on here is that we have started talking with Angie about how this might help with her work with the flagship project too. So we're trying to integrate with the different activities that are going on with SpectrumX. Some team acknowledgements. Manisha, of course, Mohammed Rahman, who developed SIGCAP application, was a great resource for us, and then obviously developed the initial prototype of what the website is today. And then my team, David Pettifor, DK, who is here at the table as well as part of Flagship Project 2, were the primary technical leads on it. And then Callie and Melissa from our CRC team played project management roles and product management roles. And with that, come see us at the poster session at 3:30, and I'm happy to take questions.
Thank you. We can fit in maybe one question if there is. Yeah, Manish. We shouldn't have a question.
More a comment than a question, and more a comment than a question. By the way, great work. 16 million data points and more coming every day is great. Please do not, if you get requests from industry, don't automatically approve it right now. There is huge amount of interest from industry in the data we've collected. They charge a lot of money for it. We need to work out how we want to address giving industry access to the data. Anybody from SpectrumX? No problem. Just wanted to let that.
Great.
So let me ask a quick question while I'm here. Is there a path if somebody wants to, get their own Android phone, download the app and start contributing data? Is that a?
Yeah. The short answer is yes. If anybody has an Android phone and would like to onboard to that, the answer is yes. I will leave it up to Manisha and Mohammed to say which device tiers are good for it, what type of antennas are good for collecting that. And then I know that Mohammed does do some routing of the dedicated Android phones, but I don't think that's necessary. But I will leave it to my two colleagues to answer that question.
Scott, do you have something?
I was just gonna say I've been running it for 2 years on my Pixel 7. So yeah, I've been running SigCap for the past 2 years on my personal Pixel 7, and it's easy to do. And so anybody that has an Android phone, I think reach out. It's pretty straightforward.
Great.
Awesome. Thank you.
Thank you.
Moving on, our next presenter is Laila.
Okay, thank you for having me here. And I'm going to talk a little bit about the circuits that we've been designing to complement part of the flagship one project that we are working on phase arrays. And yeah, let's just start first. I want to say thank you to all of the students that are worked on this project, Alec, Sophia, and Nathan. And of course, Professor Zoya Popovic that has been supporting me in this project. So basically the overview is coming up with new integrated circuit architectures that can help interference suppression in the 7 to 8.4 gigahertz bandwidth. So here what you see, let me see if we can put how can I put the pointer here? Sorry. Yeah. I can use the mouse, yeah. Sorry, I thought that the mouse was not working. So basically, the idea here is having an array of antennas that you make some analog beamforming by impinging some phases and amplitude, and then you can start your first level of interference suppression by the beamforming network. So here you have some target communication, interference in frequency 2, interference in frequency 1, and this first level of interference suppression starts from the propagation domain. So then we have, I'm going to show you some 4x4 integrated Butler matrix. Let's go back. Some switch designs, some high isolation switch design. Also, we are talking about the receiving path here, some active tunable notch filter that it's a new topology that we are working on, and also to complement some integration of tunable oscillators. Basically, it's not a VCO, but it is a tunable oscillator with a low phase noise, and all of that will help with the signal, the cleanliness of the signal downstream. So here you have the first taped out structure that's a Butler matrix. What you're going to see here, what you see here is, as you select one of each those inputs, you have the 4 outputs that will impinge some progressive phase shift, and with that you can create or adjust some nulls or increase the gain towards some direction. This was taped out in the PQG03 gas process. We want to say thank you to Win Semiconductors because they've donated a bunch of runs in gas and gallium arsenide and gallium nitride processes. And this is some of the results here. You can see that matching at this point is super important because you don't want to have any reflections and having some degradation in isolation in between the ports. So you can see that basically all of the ports are matched under minus 28 dB. And here you can see, I can send you more information about that, the insertion loss and progressive. Phase shift is very flat over the bandwidth, very like well controlled. So here you have somewhat of the specifications that we have now. And also we've designed and taped out a traveling wave high isolation GaN switch. So what is the purpose of using GaN? When you have a bunch of like a lot of interference, you may have some saturation in your receiving path. So what we want, and mainly when you are dealing with transmission and reception, you want to have some high isolation in between both path. So here you have the input port, and what you see here is a sequence of transistors that are connected in shunt and in series, and that will provide, besides high power, higher linearity, it also provides some high isolation. And here what you can see is the insertion loss in blue, S11 matching in blue, in red, and in orange. Orange, of course, this is a reflective switch, and the next step will be an absorptive switch. So you can use it with the Butler matrix. And here you can see the isolation performance beyond minus 40 dB. Next circuit, it is a tunable notch filter. What does that mean? That means that you can basically place a notch over the frequency, and if you have some source of interference, you can filter that out. So this is basically composed of, you have an input. This is the input, and then you split out in two paths. You have LNAs to amplify and to compensate for some loss that you have in the delay line. And with that delay line, when you play with those delay lines, you can basically change the notch position. Also, we have a variable attenuator that you can control the depth of the notch and the level of attenuation. And all of that will be summed back at port 2. And this is what you can see here is basically the matching over the ports, and some of the notches being developed. And this is, for instance, is the difference of the minimum the minimum attenuation level and the maximum attenuation level that you can have with the attenuator. And besides of that, we integrated with some parts that we had a VCO where you were integrated one gas HBT oscillator, or the core of the oscillator, with a 3D glass, basically an LC resonator. And what does that give to you? The glass resonator, it is a higher Q resonator if you compare to, for instance, to some very integrated structures, and that can give you a lot of less loss, higher Q, so that a better phase noise performance. How does the phase noise act or affect your performance? Basically, you have less rotation in the constellation points. So basically, those are the three structures that we've developed and taped out. The contributions, of course, we have those new circuits with new approaches. All of them are intended for interference suppression with high isolation, high linearity. 3 grad students were trained and still being trained. The next steps will be measurements, system level simulations, where we are going to grab all of the circuit model, transform into behavioral model, connect all of them, and simulate a real or a complete RF front end. So new tape outs with improvements are on the schedule, and we have four leverages for this the seed proposal. one that we've already submitted to Vines, and we made a collaboration with our aerospace at CU-Boulder and Texas NAM to bring a system, a total system with RF fingerprint detection with this new RF front-end topology. We were invited to the Microelectronics Commons Swap Hub to submit another proposal that's ongoing. And also, oh my gosh, I forgot the other two. We have another proposal that we're working on with Concept Architects to use the same concept with satellite communications and a BAA, that's a broad Army broad agency announcement that they asked us to prepare a white paper to work on those RF front ends or those components and the RF front end integration for their new anti-jamming and interference suppression radios. And with that, I think that I'm in time, right? Perfect. Yeah, that's okay. That's it. Thank you.
There is any going once? All right, let's go ahead. Thank you again.
Thank you.
Yep. All right, and Cong is next.
All right, so this seed project is a bit different. It's about spectrum intelligence using retrieve augmented generalization (RAG). For those of you who use ChatGPTs and LLMs in general, you probably are familiar with this terminology. So this is work with Nick from Notre Dame and also our students Zoya and Bingyang, both of them are here, and also Michaela, who you already met in the earlier panel. I also want to acknowledge the CRC support from Caleb, Connor, Laila, and many others. Probably I missed some here. Okay, so the idea really is we wanted to basically build a more of a SpectrumX kind of a friendly chatbot, if you will, to analyze the documents. And some of you already asked earlier during the student panel that the FCC proceedings has so many terminologies, and how do I know which is which? How do I understand what is really happening? And you can try ChatGPT to answer those questions, but as we'll see later, the problem with the this general purpose chatbots is that this kind of it does not really handle this multiple heterogeneous data sources very well, especially for massive technical and legal documents. So to solve this problem, obviously, LLM can understand complex domain-specific policy languages. Also, RAG gives us a tool to basically to search these documents, to improve accuracy and transparency. So this is in addition to the basically pre-training of the language model. We want to augment it with this additional documentation. And last but definitely not the least, this agentic AI really allows us to put everything into the same framework, calling different tools to solve different problems. And all these tools over the last year or so, I would say, matured a lot in the industry and academia, so that we want to build on this to have a machine-assisted policy interpretation, so that we can actually use that to answer potential policy questions. The challenges, one is that spectrum knowledge spans heterogeneous sources. You have tabular data, you have text that's coming from unstructured these proceedings. If you use traditional RAG just on top of the LLMs, what happens is that it really just does semantic matching between text chunks. That would actually lead to failure in terms of capturing the long relationship across different places in multiple documents. The global reasoning is going to be a challenge. And the second one is when it comes to the tabular data, which happens a lot in the proceedings, especially related to the spectrum work. Different frequencies, different bands, these numbers. The precise numerical matching is a problem that would make retrieving information from tabular data extremely difficult. So what we have done in this seed project is we designed a reusable, extensible, interpretable RAG system tailored for spectrum proceedings and license data. The core contributions so far include the following three. The team has established structured database building SQL and graph corpora from the unstructured FCC and TIA documents. The second is the benchmark dataset, which I'll just talk briefly. That gives us expert validated QA dataset. The last one is this multi-agent RAG system that utilizes the agentic AI concept I mentioned earlier that can integrate the tabular and graph retrieval for accurate answers. So let me expand these three components one by one. The first is the database construction. So I think the figure here probably says the best. We basically construct the SQL data table for every data type, and then separately we have a graph corpus for each proceedings policy files that would allow us to do high-level multi-document retrieval. And the advantage is really this framework is easy to expand. We can potentially grow this to incorporate other data or proceedings. The second one is the benchmark data set. So this is the first, as far as we know, expert validated benchmark for spectrum-related QA that covers diverse query types that integrate heterogeneous policy and license data. And the last one is this multi-agent RAG system. So this is the overall framework. There is a supervisor agent that really routes the tasks based on the different incoming tasks. It's going to call on one or multiple of the kind of a subsequent agents. We have SQL agent that mostly handles our tabular data. We have a compound agent that actually can handle the policy and the policy agent. That's the second one that uses graph rack to basically to look for information in the documents. The compound agent essentially combines the two. And depending on the specific task, we may call one or multiple of these agents to perform the task. We did some evaluation using our method, this agentic RAG method, with some clear obvious baselines. One is the so-called web search RAG. This is essentially think of it as your ChatGPT with a web search capabilities. That's actually what we do nowadays. If you go to ChatGPT, you type questions, and you can explicitly ask it to basically search online, and that's the first baseline. The second is a naive RAG. Essentially, this is just using the RAG system as is, and basically incorporate these proceedings. And last one is ours. So this really helps answer different questions that we can achieve the highest success rate again in this particular test, and that is much better than the existing RAG baselines. So the following are kind of three test cases that kind of give you an idea really what happens. Again, this is a side-by-side comparison. So like if you ask a question, what companies are using the millimeter wave service, essentially? What you'll get for the first column is basically what you'll get from ChatGPT plus some web search, giving you these results. Naive RAG in this case wouldn't be able to most of them actually naive RAG examples in our test cannot really answer the questions because of the information is not sufficient. And our method essentially can basically, have a way of, routing into the corresponding agent and then look for the right answers throughout the document using techniques such as graph RAG. I'm gonna actually skip probably all the details. What I want to talk about is really, so the students have put together a live demo. This is going to be this afternoon in a poster session. So I strongly encourage you to come and talk to Mariya and Zoya, and they're going to set up a poster to explain the techniques, the details of what I just described here. They're going to have a laptop just on the side so that you can try on this this chatbot, and also you can try it yourself. One caveat, though, is that we are not OpenAI or Google or Meta. We don't have the computation resources. So right now, the demo that we can try cannot really kind of simultaneously sponsor many users at the same time. So if you log on to this website, try it out. If you get slow responses, okay, don't yell at me. Just be patient a little bit. Try it later when nobody's using it. So another thing here, though, is also what we did. This is not entirely to the end user. So if you actually try this, you will see actually what the agents output. So we're giving you some of the details like how this actually operates. if you are typing some questions, it's going to show that what agency is doing step by step. So you not only just get the final answer, but also see, what's really happening under the hood. One more thing I want to mention is obviously to follow up this. This is, as I said at the beginning, it's a little bit kind of unconventional project, but we are hoping to expand this to leverage more funding opportunities. We have been, utilizing this to try to seek more funding opportunities. Also, students are doing some kind of branch out work on this. We have been hoping that, in addition to FCC and AKI documents, can we do more? And we'd like to talk to if you have any interesting ideas that, maybe we can grow this more. Okay? Thank you.
All right. Yeah, why don't we save questions for the poster and live demo and keep moving because we're running over our time already. I am interested to see how well this will do in this 200-page satellite NPRM. Can you give me the Cliff Notes version? That would be great. All right. Our final presentation is from Prashant, who's also online. I'm hoping the audio is... We'll see. Okay. Prashant, you there?
Yes, I'm here. Can you hear me? No.
How about on here? Is there a place on here? Give us 1 second.
Sure.
Scroll the way up on the laptop.
Yeah. No, that's no, we don't want that one.
Not good enough.
Where's Zoom? Is Zoom on here? Or no? Oh no, so you didn't join Zoom on this.
Yeah, it's on. Zoom is but I think we might have to do.
Okay. Yeah.
So zoom out.
How do I get out of that?
So zoom out. Sorry. Yeah, there we go.
All right. Yeah. Let's go ahead. Speak
Okay.
loudly.
I'll try. Can you hear me?
Yeah, you're fine.
Yeah, I'm fine. Okay. First of all, my apologies. I could not make it in person. There's also some construction going on outside, so you may hear that more loudly than my voice sometimes. My apologies for that. So this is a project that we started early this year on Byzantine fault tolerance models for distributed coordination and dynamic spectrum sharing. My colleague here at the University of Pittsburgh, Amy, is doing a lot of the work here, and I'm working with her on the spectrum pieces of it. Next slide, please. So the reason for doing this project is that increasingly, a lot of the spectrum bands, there is some kind of coordination and sharing that is happening. CBRS is the classic example where we have the three-tiered system with PAL, GAA. There is the spectrum access system, which is run by third parties like Google and Federated for dynamic coordination. They also have deployed all these environmental sensing capabilities along the coast to detect incumbent usage, and so that they can evacuate the other users in the system who are not the incumbents. In the 6 gigahertz bands, for standard power operation, automated frequency coordination is required in the US to protect the incumbent services. And more recently, in the 37 gigahertz bands, even though this is not very widely deployed, and so a lot of the coordination is happening through the FCC, there is this opportunity to have some coordination between users of the band. It is right now first come, first serve, which is whoever gets the license first and deploys it first has priority. But one can imagine that these kinds of coordination regimes will become more and more important in the future. Click, please. I think there's an animation here. I hope. Yeah, so another example is Ofcom did its millimeter wave auction recently, and that also requires some coordination with incumbents. Next slide, please. So this coordination problem is fairly complicated, and we are addressing only a small piece of it in this seed project. The technical challenges range from how best we can make spectrum allocation decisions, how can we ensure high performance, what are the institutional challenges, and what are the logistical challenges. But our goal in this project is to look at the sub-bullets in the first technical challenge, which is these coordination organizations or infrastructures could be potentially deployed by competing entities. Like Google and Federated is doing this as an example, but we are abstracting this problem into a situation where spectrum sharing has to be done. There are parties which are providing services for coordination. These could be the users themselves. These could be third parties. These could be incumbents. There are many different models that we can consider there. Not only do we have this problem of different entities offering these coordination services, we also have potential problems with fault tolerance, where the infrastructure that has been deployed in order to make coordination easier and to make it trustworthy can experience crashes. There may be all kinds of errors like measuring interference. There could be security issues and compromises. There are all kinds of reasons why these things may not work as expected. I think some of you might have noticed that today we had this huge event with AWS where many websites were not available. We are having some problems at Pitt as well because of the crash of AWS in Canvas. So that is the goal of this seed project, which is to look at these fault tolerance issues in spectrum sharing. Next slide, please. So the model that we are looking at is called Byzantine fault tolerance. This is something that has been explored in the distributed computing community for a while now. Much of the work in this space is more theory and formal methods, although there are practical applications of BFT models like we see in cryptocurrency and blockchains. And the idea here is that up to a certain number of nodes that are part of this spectrum sharing infrastructure might behave arbitrarily. So that's why we call it Byzantine. And there's a threshold number for this, which is F. And in general, without going into all the nitty-gritty details, as long as the rest of the nodes are doing the right thing and they're following the protocol specifications correctly, it is possible to tolerate F Byzantine behaviors out of 3F plus 1 nodes. This is the general high-level idea. There are, of course, nuances here. There are models that can tolerate higher numbers of problems with some trade-offs. So these are the things that we are exploring in this seed project. Next slide. So our contribution here is to map the spectrum sharing coordination problem into BFT. We have done this in a recent TPRC paper. What we have done here is that we have broken up this problem into 4 categories: the system model, the organizational model, the fault model, and the performance metrics. So to give you an example, if you look at the fault models, there's a tree that is shown here in the top right. So there are many different fault models depending on the infrastructure that has been deployed. So there are servers that are making decisions about how to make spectrum allocation grants. There are sensors that are sensing the environment to see if there are any incumbents or users with higher priority. Users themselves might be behaving arbitrarily. So there are many different categories of faults that could occur, and these are just the fault models, and they affect the performance metrics, and they are also dependent on the system models and the organization models. So our contribution here at the moment has been to take the spectrum sharing coordination problem and map it to explicit and concrete BFT models. And by doing so, we are trying to highlight the different design possibilities that we can do for spectrum sharing. What are the trade-offs when we are considering fault tolerance versus, say, spectrum utilization or other kinds of issues? For example, we can make it extremely fault tolerance, but the latency in providing spectrum grants or in evacuating secondary users when incumbents need the spectrum, these are all issues and performance metrics that we need to take into consideration. Next slide. So I'll quickly summarize this work. So what we have done so far is develop 3 what we call as agreement approaches. These are like the consensus algorithms in blockchains. But in our case, we are looking at a centralized approach where there is one logical entity which is making decisions on how spectrum grants should be made. We could also split it into regional organizations which make the localized decisions. But however, at the regions where they have overlaps, we need to take some special consideration as to how to do this in a fault-tolerant manner. The regional model is useful because it reduces the latency. The other model that we are looking at is to make it completely distributed, where people can pop up their own infrastructures for spectrum sharing. The question now would be a coordination between the distributed infrastructures. For now, we have a PhD student who is looking at the sensor deployment and how that might affect the fault tolerance. So we're looking at two different models where the sensors are globally reporting to all the different owners of the infrastructure, which means that they share the sensors essentially, or if they are deploying their own sensors. So there are different trade-offs when sensors are shared by different infrastructure deploying organizations versus them deploying their own sensors. There's an undergraduate student who is looking at conflict graphs to see how best to grant the spectrum, when the servers are making decisions on making spectrum grants. These could affect the fairness in allocation, so that's another problem that he's looking at. And there are two publications, one which has been accepted, the other is in preparation right now, which I have listed there. Happy to take questions.
All right, thanks, Prashant. We are going quite late, so I think to keep things moving along, maybe we'll take questions offline for you too. I'd just like to thank everyone. I thought that was a great set of seed projects. I think it really highlighted the sort of diversity of work that's going on within the center, and it was also really nice to see. I think most of these seeds did, blossom into something, which is the intent. We do have another round of seed funding. People have submitted proposals. We have reviewed most of those. We are close to being able to announce. Hopefully tomorrow we will do that in the morning, so give you a reason to show up if you submitted a seed proposal. And with that, I will stop. Let's thank everyone again.